Welcome students. So today we will discuss symmetric random walk. This one we have discussed before in FFM, the random walk. You can consider this is a discrete case of what we actually intend to study is a Brownian motion. Okay, the Brownian motion is the continuous case, but symmetric random walk is very similar to the Brownian motion. So we first review the symmetric random walk. We discuss some properties of symmetric random walk in details and the expectation and all, and then we gradually move into the Brownian motion. Okay, so what is a symmetric random walk? As you know, we toss a coin randomly. Okay, we toss a coin and then the outcomes are the omega. So we have omega 1, omega 2, and so on. Just a second. Okay, so we toss a coin randomly, and we have this omega 1, omega 2, omega 3. These denote the outcome. Okay, the first one, second one, and third one, and so on. Okay, so this omega 1, this one can be either H or T. Okay, all of them are either H or T. So corresponding to these values of omega 1, if the j equals to 1. Okay, so if omega 1 equals to H, we consider x1 is equals to 1. If omega 1 equals to T, we consider x1 equals to minus 1. Okay, so we get a sequence of random variables xj. Okay, now corresponding to these values of xj, we define a sequence of random variable we can say is mn. This one will later be called the random walk. So how we define the mn? The m0 is 0. So we start from level 0, and then mk we define as summation j equals to 1 to k xj. That means if we have m1, it is x1. If we have m2, it is x1 plus x2, and so on. So um, in this process, if the probability of head, so this one is the probability of head. Okay, this is the probability of head, this is the probability of t. If these two are same, then we call this is a symmetric random walk. So in our course, in our future correspondence, we always consider a symmetric random walk p equals to q. Okay, so whenever we get a p minus q terms, we can consider this is equals to 0. Okay. Okay, so what is meant by increment? Okay, what is increment? Increment means we have increment. Okay, increment means suppose we have a time t and it is less than time s, then the mt ms minus mt, this is called the increment. Okay, so if you consider formally, suppose 1 2 3 4 5 6, starting from 0 0 1 2 3 4 5 6, this is the whole sequence, and then you consider only the odd number. So consider, suppose 0 is the first element, but then the second element is maybe the second element is also 1, but the third element is no more 2, it's 3. Okay, then the fourth element is no more 4. Okay, no more fourth, it's fifth element. Okay, and so on. So what we do here is something like this. So we have starting from suppose 0 1 2 3 4 5 6 7. We consider this is k0, this suppose is k1, then maybe this is k2, and this is k3, and this is k4. Okay, we can do this. So that k0 less than k1 less than k2 less than k3 less than k4, and so on. If we want, we can consider this is not k2. Okay, suppose this one is not k2, we consider this is k2, then this becomes k3, and so on. Okay, this is also another example of subsequence of the original sequence. Okay, this is the original sequence. So now we consider, sorry, so now we consider mk1. Sorry, you consider this one first. So we consider the increment mk1 minus mk0. Now if k0 is equals to 0, then m0 is equals to 0. So this one is nothing there. Okay, so this one is nothing there. So that's why we write mk1 only. Okay, we don't write the mk1 minus mk0 as the first increment. The first increment we can just consider mk1. The second increment will be mk2 minus mk1. The third increment will be mk3 minus mk2, and so on. The last increment will be mkm minus mkm minus 1. Okay, just for your information, mkm minus 1 and mkm minus 1, these two are not same. Okay, these two are not same. Okay, so now if we consider, okay, suppose if we only consider mk2 minus mk1, then what we get? Or if we consider even easier, if we consider m2 minus m1, what we get? M1 is x1 plus x2, sorry, x1, only x0 plus x1, so it's only x1, and then the m2 is x1 plus x2, so m2 minus m1 will be only x2, right? So if we take the expectation of m2 minus m1, it's just expectation of x2, right? So if we consider mk2 minus mk1, it will be xk1 plus 1 and until x, so summation, everything is summation, summation xk2. Okay, so that's why we write summation xki plus 1 until ki plus 1. Okay, so how, if we consider the expectation here, if we consider the expectation, how expectation of this means expectation of this whole thing, so it's actually expectation of xj, right? Okay, so if you go back to the previous one, go back here, maybe we discuss these things first. So you consider expectation of xj, expectation of xj square, and maybe expectation of xj xk. Okay, so first xj, expectation of xj. What is the expectation of xj? You have a variable xj. The value can be either 1 or minus 1. The probability is p multiplied by 1, and the probability of minus 1 is q multiplied by minus 1. So it is p minus q equals to 0. If you consider expectation xj square, what you get? The value is either 1 square or minus 1 square. The probability is p or the probability is q. So it's actually p plus q equals to 1. Okay. Similarly, if you consider expectation xj xk, the xj value can be either minus 1 or plus 1. The value of xk can be either minus 1 or plus 1. So if both xj and xk take minus 1, then we get a minus 1 minus 1. The probability is q square. If xj xk both are plus 1 plus 1 plus 1, that means both of them are head, its probability p square, plus suppose the xj has 1 value and the xk has a minus 1 value, that means it is multiplied by pq, plus if xj is minus 1 but xk is plus 1, this is also the probability pq. So if you add them is q square plus p square minus 2pq, that means p minus q whole square, so it's equals to 0. Okay, so we get expectation of xj xk, expectation of xj square, and expectation of xj. Okay, expectation of xj. That means if we consider expectation of mk, it will be summation expectation xj, right? If you consider expectation of mk, that means expectation of summation xj, that means summation of expectation of xj, so it becomes 0. Clear? Now if you consider expectation of mk square, what you will get? Maybe I write here. Okay, so you consider expectation of mk square, that means expectation of summation xj, j equals to 1 to k, this whole thing square. So you get a expectation summation xj square plus twice expectation summation xj xk. Okay, so what you get here, this one becomes expectation of summation 1, right? This one, the value is 1. The value is 1. So you get this one equals to expectation summation 1. So what you get is summation, sorry, expectation summation xj square. So you get summation expectation xj square. So it's summation of 1. So you get this is equals to k, right? And this xj xk is 0. So expectation of mk square is only equals to k. Clear? So all these things clear, then we can proceed with the increment. So if you consider expectation of this mki plus 1 minus mki, we get expectation of xj. J is ki plus 1 to ki plus 1. So this one becomes all of them are 0. So you sum it, you get it 0. Okay, so this one is 0. Okay, now what is the variance of mki plus 1 minus mki? It's so again the popular formula. So if you have a variance of random variable x, it is expectation of x minus ex whole square, which can also be written as expectation of x square minus expectation of x whole square. Okay, so if you consider expectation of x square, you already know this is equals to k, right? So this one is k. Okay, maybe you forget all these things. You write it easier is if you consider ms minus mt. Okay, this one. Okay, this one ms minus mt. So so uh, if you consider the expectation of ms minus mt will be summation of xj, j equals to t2s, which will be 0. Now you consider the variance of ms minus mt. Okay, so this one means expectation of ms minus mt minus this one whole square minus expectation of ms minus mt is equals to 0. This one is 0, right? This one is 0, so it's only expectation ms minus mt whole square. So how to find this ms minus mt whole square? This means expectation of summation j equals to t until s x j square. This one you already found, this one. Okay, so it's this one equals to k. Okay, so if you have t minus s, if you have t and s, you will get it as s minus t. Okay, it's summation of 1 t to s, so it's s minus t. Okay, so once you have this, if you consider now the s is actually ki plus 1 and the t is actually ki, you just change the s and t, you will get this, right? Ki plus 1 minus ki. Okay, so that's the formula, the variance of increment and the expectation of increment for a symmetric random walk. Always remember we are dealing with symmetric, so it's p equals to q of case. Okay, next one. So martingale property of symmetric random walk. This one also we have done before. We just redo the same proof a bit different way. We consider the increment. Okay, this one is ml minus mk is the increment. Okay, so we consider expectation ml given fk. This is the information at time k. We are trying to find out the prediction of ml. What we do, we write ml equals to ml minus mk plus mk. Okay, that's the trick. That's the trick. Okay, last time was different way. This one is the trick. Now we know already the expectation of the increment and variance of the increment, so we try to use that because in Brownian motion we follow the same rule. Okay, it's the same proof. So once we have expectation ml minus mk given fk, because this one is independent, right? Ml minus mk, the value depends on the outcome of the k plus 1 coin toss, k plus 2 coin toss, and so on. It does not depend on what happened at the kth coin toss. So this one is independent of fk. So if we write this expectation ml minus mk given fk, or you write expectation ml minus mk, it's the same thing. Okay, it's the same thing. These two are equivalent, right? because these things are independent of the kth coin toss. Okay, on the other hand, if you consider this expectation of mk given fk, this value is already known at time k. So we just have mk. So now you have expectation of any increment is equals to 0 is equals to 0. So you have only mk. Okay. So that's how we have a symmetric random walk is a martingale. We don't have this property for asymmetric case. Okay, we don't have this property if p is not equals to q. Okay, this one is not in general. It's only for symmetric random walk. The quadratic variation we define this way. So we first we denote it by mmk. Okay, mmk. This is the notation. How it is defined? It is defined as summation of mj minus 1 whole square. So each of the increments, their difference whole square. Okay. So what is mj minus 1? It is xj. Okay. What is summation xj square? Is 1. So summation j equals to 1 to k, xj square means summation j equals to 1 to k, 1. So it will be equals to k. Okay, you understand, right? It's if we have xj square, the value is always 1. So if you take a summation j equals to 1 to k, you have a summation j equals to 1 to k. So you have k. Okay. So that's why the quadratic variation of a symmetric random walk is equals to k. Okay. So what's the difference between variance and quadratic variation? The variance of mk, because you see the values are same. Okay. Can you see the value is same because we have expectation of maybe mt. Sorry. If we have mt minus ms, okay, so means t is greater than s in this case. So if we have expectation mt minus ms, we have equals to 0. Okay. So if we consider s equals to 0, that means the m0. Okay, m0 we already know the m0 is equals to 0. So if we consider s equals to 0, this one is gone, nothing there. So we get expectation of mt equals to 0. Okay. Similarly, we have variance of mt minus ms equals to t minus s. If we get s, if we take s equals to 0, so this one is 0, this one is nothing there, and this one is 0. So m0 0 means this one nothing there. So variance of mt is equals to t. Okay, so you see the variance of mt equals to t and the quadratic variation of the symmetric random walk until time k is k. Okay, so they are similar, they're the same value. Okay, but what's the difference? The difference is that, as you can see, when we consider the variance, we consider the probability, but when we consider the quadratic variation, we don't consider the probability. Okay, so the quadratic, so as you can see from here, if the random walk is not symmetric, this would affect it. Okay, the variance will be affected, but compute the variance of random walk only theoretically, because it requires an average over all paths. But mmk is computed along a single path, no probability involved. Okay, that's the main difference between variance and quadratic variation. Okay, yes. What is a scaled symmetric random walk? If you look at the random walk, when we defined last time, the random walk is something like this. Maybe we have um like this. Suppose this is level 0. This is level 1, level 2. This is level minus 1, minus 2. So suppose we have a random experiment and we get a age. Sorry, we get a we get h t h h. Okay, that means we have h means 1. Sorry, we have 1 minus 1 1 1 and so on. Okay, so it's you can see it's like this one is level, the starting level, then the next level is somewhere here. Okay, the next time is somewhere here, time t equals to 1, then and so on. Okay, so you want to, what you want to do is you want to draw something like this, the same thing, the same outcome, we just want to draw something like this, very close. Oh, we want to draw very close, so it's like maybe like this. Okay, we want to draw something like this. So what we want to do, we are trying to scale the thing, the time we want to move it, the not the time, I mean the when you talk about the mn t, okay, mn t means at time t is actually multiplied by mn, by n, so it becomes mn t instead of mt. So what we are doing is to approximate a Brownian motion, we speed up the time and scale down the step size. So we don't draw we don't draw like from here until here, okay, we draw until here only. The scale size we are reducing, so we divide by root n. But the time is from, suppose last time is from here until here is time 1 2 3 4. Now from here until here we already reach time 4, so we multiply by the n. Okay, the time we multiplied by the n. Okay, this one is called scaled symmetric random walk. Okay, what's the main thing you have to understand here is that the mt must be an integer. Okay, I think we defined it, next page, huh? So nt must be an integer. When we defined random walk, the n must be an integer, right? So in here, the nt must be an integer. If it is not an integer, then we have to do something. Okay, we have to approximate the thing. Okay, so anyway, it's not important, but you just have to remember that nt is an integer. So when we take the n tending to infinite, we get a Brownian motion. Okay, we have very small differences, then it's something like a continuous case. Okay, so this is a nice picture. So you can see is a W100. Okay, W100. So here it's a part of W100 up to time 4 is generated by 400 coin tosses with a step up or down of size 1 by 10 on each coin toss. Okay, so this one 1 to 4, 1 2 3 4, the time is actually 4, but when we have the scale symmetric random walk, it's actually is like 400 coin tosses involved. Okay, the scale symmetric random walk has independent increments. The properties are all same. So if you consider 0, t0, t1 less than tm such that each ntj is an integer, then these are the increments and they are independent. And we have expectation of the increment is 0 and variance of the increment is t minus s. The next property will be the martingale property, the same proof. So you just write down the same proof. Okay, exactly same proof. You just instead of mnt you just write mn, you just write wnt, otherwise it's same thing. Okay, the next one is the quadratic variation. There's a slight difference here. Okay, I explain the thing is if you consider w and t, basically what you want to do is taking summation j equals to 1 to t, right? It's not nt. In a natural way, it should be j equals to 1 to t, and this is wnj minus wnj minus 1 whole square, right? It should be. But the problem is when you consider wn, this one is j and this one is j minus 1. The problem here is the wn, if you consider wnj, it means 1 by root n m nj. The problem is the nj, you don't know whether it's an integer or not, right? Similarly, if you consider wnj minus 1, you do not know the mnj minus 1 whether this is a integer or not. So what you want to do here is you just modify the thing a bit. The summation you don't take, over j equals to 1 to t. You take j equals to 1 to nt, and instead of writing j here, you write j over n, so that it becomes m n j over n. So it becomes mj. J is integer. Clear? Should be clear, right? This one is wn j over n, so it becomes 1 by root n m n j divided by n. So the n cancel out, is mj. Mj, the j is integer because j is the running index. So mj is, j is integer, mj we know. Okay, so you can write down. Okay, and then afterwards you already know how to do it. Okay. Okay, the central limit theorem states that fix t greater than equals to 0 as n is very very large. The distribution, okay, when I say very very large means n tending to infinite, okay, So if n is very very large, the distribution of the scaled symmetric random walk w and t evaluated at time t converges to the normal distribution with mean 0 and variance t. It's very important. So when we consider the scale symmetric random walk and this one is the scale symmetric random walk and the n is very large, then the distribution is a normal distribution with mean 0 and variance t. Okay, so next one is the Brownian motion. We define a Brownian motion. How we define it? It's just a simple thing. It's a continuous case of whatever we learned so far. Okay, from the symmetric random walk and scale symmetric random walk. So we define over a probability space omega fp. For each omega, small omega belongs to capital omega. Suppose there is a continuous function wt such that w0 is equals to 0 and the increments are independent and the expectation of increment is 0. The variance of increment as always is like variance of maybe I write it this way. This will be easier to understand. Variance of wt minus ws is equals to t minus s. Okay, like before. So how many properties? The first property is w0. W is continuous function. First one is w is a continuous function of t. w0 equals to 0. The increments are independent. The increments expectation, the mean is 0. The variance is t minus s. Okay, so total you can say is 5 properties of Brownian motion. So whenever we are given a Brownian motion w, we always know these 5 properties holds for wt. Okay. So now you can guess it. When we define the Brownian motion from the scale symmetric random walk, we will check all the properties. So far we checked for scale symmetric random walk, namely the quadratic variation and the martingale property. The martingale property, the proof is exactly similar. The martingale property is exactly similar. Okay, this one I come back later. So the martingale property is exactly similar, and then we have the quadratic variation. The quadratic variation will be WWT equals to T. Okay, so like always is the random walk, symmetric random walk, and then the scale symmetric random walk. Both of them are same, and same thing happen for the Brownian motion. The quadratic variation of WWT equals to T, and the Brownian motion WT is also satisfy the martingale property. Okay, and then we have few more things. WTI has mean 0. The covariance of WS and WT, you can find out expectation WS WT will be expectation WS. So the WS WT, so here whenever you got a problem with expectation of some Brownian motion, you always try to write this part as increment. So WS WT you write down as expectation WS multiplied by WT minus WS plus W square S. Okay, so you can write down expectation of WS here, expectation ws, expectation wt minus ws, okay, and plus expectation w square a. So this part is becomes 0, and therefore it is expectation w square is only. Okay, now the thing is, if you consider variance of the variance of ws, you will get expectation of ws whole square, sorry uh, okay, expectation ws whole square and minus expectation of ws. Okay, this part is equals to 0, so it's expectation ws whole square. So expectation w square is equals to variance ws, and variance ws you already know is equals to s, so this one is equals to s. Okay, so you can see that if I should write here the s is less than t. Okay, if s less than t, then we have expectation ws wt equals to s. Okay, if t is less than it, it will be t. So you can just apply this and then you can find out the covariance matrix. Expectation w square t1 will be t1. Expectation wt2 wt1, t1 less than t2 means this will be t1. Similarly, if expectation W T1 W Tm, T1 less than Tm, it will be T1 and so on. Okay, so this is quite easy. The filtration of Brownian motion, as always, when we consider a filtration, means it's a sigma algebra. Okay, it's a collection of sigma algebra, and then we have like last time we write sigma, like last time we write the if S1 subset or sub sigma algebra of fs2, right? So uh, we say information accumulates, and then adaptivity means the sigma of x, last time was sigma of x is subset of fs, right? So now it's adaptivity is sigma of w is under fs1. So at the time s1, the w value, w s1 value is already known, and independence of future increments means if we have wt, so it means, okay, maybe I write down. So it means when you consider expectation wt minus ws and sorry ws given fs, okay, this is actually same as expectation of wt minus ws. Okay, so this is meant by the filtration of Brownian motion. Okay, martingale property has been done. Quadratic variation is this, and then okay, we discuss about the proof. We need few things, so we discuss about the proof. So before that, I just tell you. So when you prove this WWT equals to T, the short form is like this: dw is equals to dt. When we prove this, we also prove dw dt equals to 0 and dt is equals to 0. Okay, I have already discussed this in class. I hope you remember. Okay. Uh, so this is called normal kurtosis. Suppose x is a normal 0 sigma, means mean is 0 and variance is sigma square. Then we define the moment generating function is phi u. Then the nth moment will be expectation x minus ex whole to the power n. This one is given by phi n 0, the differentiation of phi n times phi n 0. So we can find out the phi n 0, and then we can find out the nth moments. Okay, so the first moment expectation x minus ex, expectation x minus ex whole square, and so on. Okay, so you can see its value 0 sigma square 0, 3 sigma to the power 4 0, and 15 sigma to the power 6. Okay, so you can, you should note here the expectation x is always 0 here. Okay, this one is all 0. This one actually is not here. Okay, because we consider the mean is equals to 0. So this one is actually not here. Okay, anyway, so I think the most important is this one. Okay, we use this one. So how we prove the quadratic variation is equals to t? We first consider the q pi. By the notation q pi, we mean is summation j equals to 0 to n minus 1 wtj plus 1 minus wtj whole square. So expectation of wtj plus 1 minus wtj whole square, we can find out is tj plus 1 minus tj. And therefore, if we take the summation, we see that the expectation q pi is equals to t. And then we find out the variance of wtj plus 1 minus wtj whole square. So we can see that this one becomes using after using this fact, we see that this value will be uh, this one 2 tj plus 1 minus tj whole square. So we take the summation over here, it will be less than equals to 2, so 1, so this one is actually, we can write down tj plus 1 minus tj plus 1 minus minus tj, so minus tj. So we have one of these, we can write one of this is, this is the maximum one. So this is less equals to norm pi and tj plus 1 minus tj. So you can write down this. Okay. So in particular, if norm pi tends to 0, this one tends to 0 means this part goes to 0. Okay. So the variance q pi is 0. So that means probabilistically we can say that the limit pi norm pi tends to 0 q pi is actually expectation of q pi equals to t. Okay. So that's why we say that the quadratic variation is equals to t. Okay, next thing we discuss is the E2 integration. So like I said, in stochastic calculus, we have differentiation, integration, and yeah, these two things mainly differentiation and integration. Okay, so this is Ito's integration. How we define the Ito integration? We will continue this one afterwards.